Okay, hey there. It's Mr. Frank. I hope you guys are all doing well. I've been thinking about each of you a bunch, and the plan for the next couple weeks will run through the energy chapters. So, Chapter 12, non-renewable energy resources, and Chapter 13, achieving energy sustainability, the future of energy. So we'll do part of chapter 12 today. Please pull up the reading questions, and I'm going to have you fill in those questions as homework. So if you can watch this and pause it and fill in the questions at the same time, that'll save you some time. Let's do 1 through 14 today, and then we'll finish on Thursday. Okay. So, non-renewable energy resources, some new vocab and some words that I'm sure you're familiar with. So, kind of spiraling back on some terms as well. Lots of terms, and we start off with just looking at the first Earth Day, which really came about in the April 22nd, 1970. There was an oil well explosion off the coast of Santa Barbara that spilled about 3 million gallons of crude oil into the ocean, oiling some marine mammals, certainly some fish, and many seabirds. And that kind of exploded in the consciousness of Americans. We're also looking at our planet and images of our planet from space for the first time, and that sort of shifted our consciousness as well, and recognizing that we're all on this planet together. So our reliance on oil and fossil fuels since the 1970s has really increased. And there can be spills and mishaps all during the process of production of both, oil, coal, natural gas. So some quick examples. We looked at the Exxon Valdez spill already, 1989. Crashed into Prince William Sound and spilled 53 million gallons of oil into a totally pure, pristine marine habitat. Caused the death of a lot of marine mammals, seabirds and the like. In 2010, we had the BP Deepwater Horizon blowout and the explosion that killed 11 workers, injured 17, 206 million gallons of oil dumped into the Gulf of Mexico. There was the BP oil refinery explosion in Texas in 2005 that killed 15 workers. And there are a number of coal mine disasters over the years. April 2010, 29 miners were killed in West Virginia during an explosion there. So, the renewable resources that we use have some problems, and we'll look at those. So, most of our energy comes from non-renewable resources. These are things that can't be replenished on a human time scale. Take, in many cases, thousands, if not millions of years to generate. And the main categories of those are fossil fuels, coal, oil, and natural gas, and also nuclear fuels. And, what affects the rate at which this energy is used? Well, availability of that, affordability of that. Of course, we look now at environmental impacts associated with these fuels. And then, look at, like, in 2005, we used 355 gigajoules per person per year. That's 5 times greater than the world average. And the US is about 20% of the world. We use roughly 70% of the world's energy. Okay, non-renewable energy resources, things like fossil fuels, coal, oil, natural gas, also nuclear fuels. Those are the big piece of the pie here, the big pieces. So fossil fuels are about 81% of our total energy mix. Nuclear has been about 6%. And, this information is a tiny bit dated, but roughly 495 exajoules, okay? Or 469 quadrillion BTUs per year. All right, distinguishing the types of energy use. So commercial energy sources are things, this is one of the reading questions, things that are bought and sold like coal, oil, and natural gas. Subsistence energy is different. That's in energy that's gathered by individuals for personal use. Things like wood, charcoal, even animal waste. Cow pies are collected in large parts of the developing world and burned as both fuel for heating and for cooking. Okay, the history of different types of fuel usage. Up until about 1875, most of the energy that we used came from burning wood. And then starting around 1875, we started using coal much more widely. Early in the 1900s, we began to start using oil and natural gas as well as coal. And those were really the primary sources of energy until the 1950s, when we started using more nuclear energy and hydropower, hydroelectricity. So in the 70s, there was a decline in oil use, and kind of the oil global geopolitical politics caused a resurgence of coal usage in the U.S. But now worldwide, it's basically oil, coal, and natural gas. Although natural gas is kind of starting to outcompete coal in many markets. What do we get with this? Well, we get work, and we'll look at that. A lot of natural gas and coal and oil is used to generate work, create electricity, and then also some waste products like heat, carbon dioxide, of course, and other types of pollutants. Okay, graph showing energy use over the many years. So going back here, we've got wood use, and then starting again in the 1875 area, a lot of coal usage. And then early in the 1900s, you see petroleum, which is oil, right? And also a big increase in natural gas. And it's really not until much later you start to see hydroelectric power and nuclear power. And wood continues in the background all the way through. Okay, this is just looking at that again. And you can see oil is the major energy source, although natural gas has been outcompeting coal more recently. So those are the top three. Okay, so we produce about 70% of the energy we need. That's been increasing. 30% of it comes from other countries. Our use varies in the U.S. Both seasonally and regionally. So you think about, the Southwest, California certainly, and then Arizona, New Mexico, Texas. Lots of air conditioning needs during the summer months. And then you flip, and the Northeast and really all the northern tier states have a lot of heating needs during the winter months. Okay. The type of energy that's used for the heating and the cooling depends on a lot of different factors, like ease of transport, how close is that fuel source to the end use, what's the amount of energy that's embodied in that kind of thing. So coal is really, popular choice for heating in the Northeast. And we do still generate some of our electricity here in the Southwest from burning coal-fired power plants. Okay. So, gasoline is really good for transportation, for moving cars and trucks, of course, airplanes as well. So it has a high energy to mass ratio, and it's relatively safe in terms of putting gasoline into a tank of a vehicle. If a vehicle's involved in an accident and the sudden impact, gasoline's relatively stable, is very often not going to cause an explosion, although sometimes that does happen. But it's certainly more stable than, say, hydrogen, for example. Okay, second law of thermodynamics. Okay, so when a source of energy is transformed, the ability of that source of energy to do work diminishes, and we'll look at that. But here we have an energy resource here, coal. It's being extracted, transported, processed, and then burned. Here's the combustion right here, and then that combustion of that coal creates electricity, and that electricity is transmitted through power lines to an end user. And all along the way, you can see the red arrows creeping out. Those are energy losses. Coal requires energy to be transported, extracted, all those things, processed. There's some loss in the transmission lines, and there's disposal of coal ash uses energy as well. Okay, so then you get to this concept, EROEI, EROI, energy return on energy investment. So you want if you're a fossil fuel or energy producer, you want a big EROI. The bigger, the better. That you make more money as a oil company if you have a lot of energy obtained versus the energy invested to obtain the fuel. Early on in the oil extraction, there were roughly about 300 barrels of energy returned for every barrel of oil that was invested in getting oil out of the ground. Now we're at a place where it's roughly 3 barrels of energy returned for every 1 barrel invested. So what that's saying is a lot of the easily affordable fuel or oil has been used, and now we're going after oil that's a little more energy intensive to get at, either because it's way offshore or it's mixed with tar sands and it has to be cleaned, that kind of thing. Okay, so public transportation is way more efficient than traveling by individual in a car. As more people go into a car, the efficiency of that car in terms of transportation goes up. Vehicle choice plays an important role. A lot of us, in the U.S. have the freedom to choose, whatever vehicle we like, and efficiency is not the main consideration for many people. As when you look at popularity of SUVs, is a good example. Okay, and legislation's gone back and forth. The idea is that miles per gallon (mpg) it should be at around 35. Recently those restrictions have been in the courts and being rolled back and forth. So something to pay attention to. Okay, this is looking at energy efficiency over time of automobiles in the U.S. So there was a dramatic increase in the late 1970s, and then it's been relatively stable till most recently. Okay, this concept of embodied energy. The sum of all energy needed to produce any product. This is energy that's actually incorporated into the product itself during the manufacturing process. And there's a carbon footprint associated with that. Okay, so when we look at the embodied energy of household items, this is further defining this concept. So you can look and see that a blender, for example, roughly 5 liters of oil are required to create a blender. Whereas you look at a larger household appliance like a washing machine, and you've got many, many, many liters of oil, okay, embodied in a washing machine. Okay, and you can look at just building materials. Some building materials like stone, you don't really have to do anything to it, not much in the way of processing. So the embodied energy in that is relatively low, but aluminum has to be, heated to a super high temperature and separated from other, elements and constituents in the ore. And so aluminum has a very high embodied energy, as does things like fiberglass, brass, lead, of course, steel. Okay. So again, thinking about embodied energy, 10 times more energy to produce fiberglass insulation and up to 64 times as much to produce foam than cellulose insulation. Okay, so you're just comparing these types of insulation for homes in terms of the vehicle. So cellulose is, this graph is showing that cellulose insulation is the most efficient. Okay, another way to think about embodied energy, the nearly 90 million new vehicles produced globally in 2014 embody more energy than all the renewable electricity produced in the world during 2014. Okay, primary versus secondary sources of energy. So primary energy sources, coal, oil, and gas. Secondary is electricity that's produced by burning those primary sources. So electricity, secondary. Okay, it's clean where you use it. Electricity is a clean source, but electricity is coming from some means of production. And we know that hydroelectric power is relatively pollution-free once the dams are in place, low carbon in terms of carbon emissions to the atmosphere. But coal, oil, and natural gas generating electricity winds up creating a pretty significant carbon impact. And the fewest number of conversions from that fuel source, it results in the greatest amount of efficiency. Okay, and talk about energy carriers. Energy carriers are things like, again, gas, liquid natural gas, propane, and even microwaves are being explored as a source of energy carrier, as a way to carry energy and provide energy. Okay, generating electricity. So just a quick graphic here that shows the entire process. So we're looking at coal as the source here. Coal gets pulverized and fed into a boiler, and that boiler generates heat. Heat is used to turn water into steam, and when that steam is pressurized, it can be used to spin a turbine, and the turbine itself can be connected to a generator. A generator is simply copper wire and magnets spinning rapidly around each other. And we know that with copper wire and magnets in rotation like that, we generate electric current and have electrons move along a transmission line. Okay, that's pretty much it. Most electricity is some form of heating water, turning it into pressurized steam, and spinning a turbine, which is connected to a generator. Okay, we covered this. There's the what we just talked about in text form. That's also one of the reading guide questions. This gives you a little sense about the rotors and the magnets in the generator itself. Okay, just a quick review with hydroelectric power. Hold on.
Oh, sorry. I didn't realize you were still doing it. Did you change the time?
Don't.